We'll do 3 solved examples today. So we are given a square matrix Q, which is positive definite, and another square matrix A of the same size as Q, which is non-singular. And our goal is to show that this block matrix here is non-singular. Now consider this block vector xy such that b times xy is 0. Now, if b is non-singular, then b times xy would be 0 only if both x and y are 0. In other words, to prove that b is non-singular, we have to show that this is true, bxy is 0, only if x and y are both zeros. So, replacing b with this expression, we get qa transpose a0 xy, which is equal to this equals 0, which implies that qx plus a transpose y equals 0 and ax equals 0. These are our equations 1, 2. Now from 1 we get qx plus a transpose y equals 0. Pre-multiplying both sides with x transpose, we get this expression here. Whence x transpose qx plus ax transpose y equals 0. Now, we know that ax equals 0, whence this term is 0. Hence, x transpose qx equals 0. Now, q is positive definite. When is x transpose qx 0? That's only possible when x equals 0. That's equation 3. X equals 0 we proved. Hence, A transpose y equals 0. Since x is 0, this term is 0 in equation 1, and so A transpose y equals 0. But A is non-singular. Therefore, A transpose y is 0 only if y equals 0. This is n. And so we just proved that x and y are both zeros. Hence, B is non-singular. Example 2, we are given a matrix A and we are given an approximate eigenvector x of this matrix A. And we have to find the best estimate of the corresponding eigenvalue. So let's assume lambda is the corresponding eigenvalue for this x, and so ax must be approximately equal to lambda x, or x lambda minus ax should be approximately equal to 0. So let's try to minimize the square of the L2 norm of this vector here. So this is what we have to minimize. Phi of lambda equals x lambda minus ax transpose x lambda minus ax, which is equal to this. Now, its derivative at the minimum must be equal to 0. So the derivative of this expression is, with respect to lambda, is this. Twice lambda x transpose x. And this is constant with respect to lambda. And for this one, the derivative is simply twice x transpose ax. And I will just assume that the Hessian is positive definite. So at the minimum, this derivative must be equal to 0, whence x transpose x lambda is equal to x transpose ax. Whence lambda is equal to x transpose ax over x transpose x. So this is the best estimate of lambda. Example 3. We are given a symmetric positive definite matrix A, and we have to show that the diagonal elements of A are all positive. AII is always greater than 0. Let's take the first row and first column and express this matrix A as this block matrix. So this is the first row and this is the first column. A11 is the first diagonal element. And we take this vector x of the same dimension as the number of rows or number of columns of A. And so let that be x1, a scalar, and x2. So x2, remember, will be of the same dimension as A22's rows and columns. Now, since A is positive definite, x transpose Ax is always greater than 0. Whence, this is greater than 0. I'm plugging in the value of A here in terms of this block matrix and likewise for x. Whence, I do the multiplication and I get this expression here is greater than 0. Now, I'll take x1 common from the first and the second term, and so I get this expression. Let's remember this expression for the next slide. So this is what we arrived at. Now, we have to show that AII is greater than 0. Let x1 be not equal to 0 and x2 be equal to 0. So in that case, this expression, since x2 equals 0, this expression simplifies to A11 x1 square is greater than 0. Whence A11 is greater than 0, since x1 square has to be greater than 0. So we just showed that A11 is greater than 0. So the element in the first row and first column of this SPD matrix A is always positive. Now, let's assume x1 is 0 and x2 is non-zero. Because x is non-zero, that would make this strictly greater than 0. Whence, plugging in the value of x1 equals 0, we get x2 transpose A22 x2 equals 0. Which means that x2 can be anything non-zero. So it means that A22 is also positive definite. This. Now, exploiting the same property, since A22 is positive definite, its first row and first column must always be positive. Whence, lowercase a22 is greater than 0. And we can proceed further. We first showed that A11 equals 0, then we showed that A22 equals 0, and we can proceed further, show A33, A44, and so on, show that all the diagonal elements are greater than 0.